Today, we are diving into an important concept in data structures, abstract data types, and their implementation, focusing especially on the sequence ADT and how it's built using arrays and vectors in C++. By the end of this video, you will understand not just how these structures work, but also how to implement and analyze them, including amortized analysis for vector append operations. So before we talk about ADTs, let us start with the basics, data and data types. You are familiar with values such as integer 5, string hello, floating point 78.190, string 25, etc. A data type is defined by three things. The domain, which is the set of possible values. Second, the operations you can perform. And the third is the rules that define what those operations mean. For example, integers support addition, subtraction, multiplication, and division, while strings support only concatenation. This structure of domain operations and rules forms the foundation for abstract data types. What we have seen is concrete representation of data type. In contrast, an abstract data type or ADT is a high-level description of a data structure. It focuses on what operations can be performed and not on how they are implemented. Think of a bank account. You know you can deposit, withdraw, and check your balance. You don't need to know the internal database tables to use it. This separation of interface from implementation is the essence of abstract data type. One common ADT is the sequence ADT, which represents an ordered collection of elements like a list. Some key operations that you can perform on sequence ADT include element at a particular location, which is to get the ith element in the sequence. Replace ix is to replace element at ith location with value x. Insert ix is to insert value x at position I. Remove I is to remove the ith element in the list. Append x is to add x at the end of the sequence. Remove last is for deleting the last element in the sequence. You also need an operation to get the length of the sequence, which is the current number of elements in the sequence. Because these operations are defined independent of the type of elements, a sequence can be homogeneous or heterogeneous. For example, arrays in C++, where you can have elements of only one type, that is homogeneous in nature. Whereas in Python list, you are allowed to place elements of different kinds, which is an example of heterogeneous sequence. A sequence ADT can be realized in multiple ways. We will see some of them now. So let us look at the first concrete implementation of this sequence ADT in C++. The simplest implementation of a sequence is an array. In the example shown, the first line defines an integer array of size 6. The second is operation storing value 10 in the first location. As we have noted, all values in an array are of the same type. The cells which are shown are contiguous in memory, and the indexing starts from 0. So array provides constant time access using indexes. The element and the replace ix operation are supported by bracket. But this particular array data type has certain limitation. It is not exactly giving you all the functionality that we have expected from sequence ADT. First is that there is no built-in support for operations like insert in the middle of an array or remove from the middle of the array. Let's address these limitations within the framework of object-oriented programming. Here is a quick refresher on object-oriented programming or OOP. First, there is this guiding principle which I really like. You don't ask first what the system does. You ask what it does it to. In other words, don't just focus on actions, think about which entity the action is happening to. In other words, don't just focus on actions. Think about which entity the action is happening to. This mindset naturally leads us toward designing objects. Next is encapsulation. This simply means we bundle data and the functions that work on that data together in one unit. Think of it as a putting both your data and its tools in the same box, very neatly and very highly organized. Then there is information hiding. This is like using a TV remote. You know which buttons to press, but you don't need to see the circuit which is inside your remote control. Similarly, a class lets us use its public interface without exposing how everything works inside. Now, what's a class? A class is basically a blueprint. It describes the attributes, also called data members, and the behaviors, also called methods, of an object. You don't get an actual thing yet, it's just the plan. And finally, an object is the actual thing created from that blueprint. For example, if the class is car, then your own car in the parking lot is an object. Now that we understand the basics of object-oriented programming, let's talk about what makes up a class in C++. First, the private section. This is where we keep the actual implementation details, the data members, and any helper methods that the outside world doesn't need to know about. You can think of it as an engine under the hood. It does all the work but stays hidden. Next comes the public section. This is what we expose to the user, the functionality. It's like the car's steering wheel, pedals, and dashboard. You use these to control the car without opening the hood. The main goal here is to make sure that even if someone knows the internal structure, they shouldn't have to rely on it. This means we are free to change the internal code later without breaking the way users interact with the class. Now let's talk about the constructors and destructors. A constructor is a special method that runs automatically when you create a new object. It's used to set things up, like giving default values or allocating resources, so the object is ready to use right after it's created. And finally, the destructor. This is another special method that's called automatically when an object is no longer needed. It's the cleanup crew. It frees up memory or closes files. We don't leave any mess behind. So to summarize, a class hides its inner workings in the private section, exposes the useful interface in the public section, and uses constructors and destructors to manage an object's lifecycle smoothly. This is what makes classes so powerful in organizing our code. So next we will use these ideas to create our own class called MyArray, which is going to overcome some of the limitations that we have noted for array earlier. MyArray bundles data, the array itself, and methods that operate on it. So this class keeps track of the actual array inside, how many elements we have added so far, and how much space we are left with. We can add functions like appendix to add at the end, elementAt to fetch stuff, and insert ix to insert an element in the middle by shifting the rest of the elements towards the right. This is where object-oriented programming comes in. We hide all the messy details inside the class so that the user just calls these functions and need not worry about the actual implementation behind it. In the example shown, my array has private variables underscore ARR, capacity, which is the maximum number of elements that we can store, size, which is to keep track of actual number of elements which array is holding. There's a constructor that takes a parameter capacity and creates an internal array using dynamic allocation using new. During creation of my array, it holds no value, size is set to 0. The destructor is called when my array object's life is over and the destructor frees up the allocated memory. In the main function, we are first creating an object ARR with capacity 50, and inside the for loop, we are appending some values in ARR. In the second for loop, we are fetching the ith element from myArray object. Here are the other member functions of the class myArray. The length member function returns the current number of elements which is stored in underscore size, which is a private variable of our class. The member function elementAt returns the ith element in the array. Next, we have replace function, which takes an index and it takes a value and replaces the value stored at ith location with x. We have then append function, which appends the x value in our sequence, and then of course it has to increase the size by 1, which is happening in the next line. And the remove last function is going to return the value which is stored in the last location, pointed to by size minus 1. And since you are removing the last element, you are going to reduce the size by 1. So we noted earlier that the default array provided in C++ does not give you the functionality of inserting a value somewhere in the middle of sequence. So now, since we are implementing our own data structure MyArray, we can write a member function insert, which takes an index I and it takes a value x to be placed at that index. So we are having two checks here. The first check is whether the array can accommodate new value or not, which is by checking if size is already equal to capacity. If that is the case, we will say that the array is full and we cannot insert a new value inside the array. The second thing that we are testing is whether the index is correct or not. So index cannot be less than 0 and it cannot be beyond size. If this is not happening, then we are going to say that the index is not valid. Now, once we have checked these two things, we are going to shift all elements starting from I towards the right hand side, which is done by the for loop. And this is going to create a room for the element to be placed at ith location. And that's what we are doing in the second last line, underscore arr I equal to x. And since we have introduced one more element in our sequence, we are going to increase the size by 1. So I'm not showing you the remove function. The remove function is going to shift the element towards left hand side, and thus this I'm leaving as an exercise for you. So MyArray has achieved most of the things that we wanted from Sequence ADT. However, we still have a serious limitation with MyArray. The limitation is that the capacity is decided during creation. And once you have created an object with certain capacity, there is no way you can change the capacity of that particular object after its creation. So this is likely to result in creating a MyArray object with very large capacity, and therefore this is going to be very inefficient from space management point of view. So how do we now resolve this particular issue? Can we do something better than this is the next goal. And in order to work on this, let us define a parameter which I am calling load factor. And the load factor is simply the ratio of the current size, that means the current utilization of the array, divided by the total capacity, the number of elements the array can hold. And we would like this value of alpha to be as large as possible. Of course, the range of alpha is between 0 and 1. So we would like it to be closer to 1. If we can achieve it, then we would have overcome this particular limitation of MyArray. So as I just mentioned, value of alpha is 1 when number of elements in internal array is equal to the capacity of the array. So okay, so far we have seen arrays and even built our own class, MyArray class. But the main issue with regular arrays was that their capacity is fixed. Once it's full, you can't just add more elements. This brings us to the idea of a vector, also called stretchable or dynamic array. It's just like any array, but it can grow automatically when needed. Here is a simple template class for vector. We are using template class T so that we can store any data type, integers, doubles, strings, or even objects. In the private section, we have got underscore ARR, which points to the actual array in memory. Underscore capacity, the current total size of that array, and the underscore size variable is to keep track of the number of elements we have actually stored so far. The constructor sets things up when we first create a vector object. We allocate an array of some initial capacity, by default just 1, and set size to 0 because it's empty at the start. Now here is the big question. We ask what happens when we try to insert or append an element and the capacity is equal to size. In other words, when our load factor alpha equals to 1 and the vector is full. This is where the magic of stretchable arrays comes in. When the vector is full, we create a new array that's twice as big, copy the existing elements over, and then add the new element which is going to definitely accommodate it. This way, we don't hit the capacity wall like in plain array. So I'll now show you how this happens. So let us take an example. Here is your internal array which is having capacity 4, and suppose all 4 cells are occupied. That means size is equal to 4. In other words, the load factor alpha is 1. And if you want to add one more value, what should you do? So as I said, we are going to create an array of size which is double the original size. Now we had the capacity was 4 earlier. So we are going to create another array with capacity 8. Now we are going to copy all the elements from the original one into the new one. So the values A, B, C and D are going to be copied in their respective locations, and then you delete the old array. Now, this is what is going to be the new internal array, which is going to have capacity 8, and the size of this particular thing, that means the number of values it is holding is 4, and it can accommodate one more new value. Once this has happened, the load factor is going to become 0.5. Now, this requires us to implement a function which is going to be private. The person who is using your vector class need not be aware of existence of this function because this is an internal thing, and this function is going to revise the capacity depending on the value which is passed. It creates a new array of the dimension new capacity, and the second part is the for loop which is going to copy the values from ARR into new ARR. Once these values are copied, it's safe to delete underscore ARR. And now your underscore ARR can point to the new array. And the capacity, if you have doubled it, it's going to become that new value. But in our case, since you are passing new cap as a parameter, the capacity is going to be equal to new cap. So now we can implement our append function, and unlike the previous case, MyArray, where we were throwing an error if the capacity was equal to size, we are not doing that. If capacity is equal to size, we are going to call revise capacity function, which we have just seen, and we are going to double the capacity. And this is going to ensure that the old values are copied in the new array and everything is in order. Now you can add the new element at the end of the ARR by doing underscore ARR bracket underscore size equal to element, and you can increment the size variable. So let's analyze what we have done in the append function. So what is going to be the range of alpha? The range of alpha is going to be between half and 1. And the value of alpha after first stretch is going to be half, the example which I have just shown you minutes back. And what is the complexity of append operation? That's the main question that we would like to now consider. So in order to do this, we are going to do something which is different from whatever analysis you might have seen earlier. We are going to not look at just one operation. We are going to look at a sequence of n append operations. So it is possible that one operation might be expensive, and we are interested in finding here that if we take a sequence of operations and then look at the total cost and divide it by the value n, then is the cost going to remain constant or is it going to depend on the value n? So let's consider a sequence of n append operations, which is adding a naught, a1, dot dot up to n minus 1. And since the cost can be different for each of this element, we are associating cost c naught with a naught, c1 with a1, and so on and so forth. So how is going to cost look like? So here is the picture. When we are adding the first element, which is at index number 0, which is shown on the x-axis, you're going to simply add it because you would have created array of capacity 1 in the beginning, which can definitely accommodate the first element. However, when you append the next value, this is going to create an array which is going to be double the size of the previous one. So you're going to create an array of size 2, and you're going to copy the old value into the new array, and that is also going to require some cost. So now the total cost for adding the element at index 1 is 2. And then since you would have doubled the size from 1 to 2, you still cannot accommodate one more element because you are having still this situation size is equal to capacity. So now you are going to further double the size when you add element at second location, which is going to create an array of size 4 and copy the earlier elements and then add the next element. So this is going to incur cost 3. But when you add one more element, since you can accommodate one more element without creating new array, your size is not equal to capacity. Fourth element added is not going to cost for the stretching part. So that is going to be operation costing you just 1 unit. When you add one more element, again you will have the situation that size is equal to capacity, and therefore the stretching is going to happen, and it's going to create an array of size 8. So the element at index 4 is going to cost you 5 units, but after that the addition of new elements at location 5, 6 and 7 can be done without incurring any extra cost. However, when you add ninth element, which is going to be at the index number 8, you are still going to have the same situation, and therefore you are going to stretch the array. So that's why you have this vertical bar having 9 units. But after that, 9, 10, 11, 12, 13, 14, 15, there's not going to be any stretching because those elements can be accommodated because your array capacity is going to be 16. So let us look at the cost function. So if Ci is cost of ith operation, it is going to be 1 if I is not power of 2. As you can observe, only when I is power of 2, the cost is different. Otherwise, it's going to be 1 unit. If I is power of 2, then the cost is going to be I plus 1, which you can easily observe from the upper chart. Now this, if you are going to do sigma for n operations, then the cost is going to be n plus sigma I equal to 0 to log of n roughly 2 power I. Why? Because if you are having n values, then how many powers of 2 are going to be there? That's going to be log of n. And if you solve this particular relation, then you're going to see that this is less than or equal to 3n minus 1. So thus the amortized cost for n operation is 3n minus 1 divided by n, which gives you order of 1. So the average cost is still a constant, which is same as what you had for the original array. So how do you handle deletions? So we were ensuring so far that the alpha, that is the load factor, is 1 by 2. But you are also going to have deletions from vector. You might remove elements from your vector. That might bring down the load factor below half. And that's something which is not desirable. So in that case, you can do the opposite of stretching, which is shrinking. So the question is, when should you shrink and by how much should you shrink? So that takes us to the question that earlier we were expecting to maintain load factor of half. Should we still continue to do so? And here is implementation of remove, which is doing the shrinking exercise, but not when the size is equal to capacity by 2, but we are doing when size is equal to capacity by 4. So when you have the situation that only 1 by 4 elements of the capacity are present in your array, then you are going to shrink. but we are not going to shrink exactly to make size equal to capacity. We are shrinking by half the capacity. That means when the shrinking has happened in the situation when the load factor was 1 by 4, the shrinking will make load factor again half. And why is that? This is a question I'm leaving as an exercise. And I'm also leaving this as an exercise that if you have both insertions and deletions, sequence of n such operations, then what is going to be the amortized cost?